Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. Let's see. So we continue our tour of quantum mechanics. I remind us again, our solution of the infinite square well, we found that allowed psi of x's took on the form for a well of width L, infinitely deep. Square root 2 over L times sine of quantity n pi x over L, where n takes on positive integers. We also have the quantized energy levels, E sub n, h bar squared, h bar squared, pi squared, n squared over 2ml squared, goes as n squared times E1. Just a quick rehash of what this looks like. I drew the first few. Psi 1 looks like a frowny face. Psi 2, frowny face and smiley face. Psi 3, two frowny faces with a smiley face connecting them. Psi 1 squared, psi 2 squared, psi 3 squared looks as such, right? This turns to this, these two turn to these two, these three turn to these three. Hopefully that makes sense. If not, I think our other lecture video should make some sense of that. Today I introduced the momentum operator. The momentum operator p sub x goes as h bar over I d dx. And so note then px squared acting on psi, while h bar times h bar is h bar squared, I times I is -1, so this turns into minus h bar squared d squared psi dx squared. Hopefully that's not terrible. Awesome. Okay. With that in mind, I wanted to see if we could calculate the expectation values of px and px squared for a particle in the ground state of an infinite square well. And so the expectation value of px then is just going to go as 0 to L. Well, remember, expectation value of f of x goes as psi star f of x psi dx. And so 0 to L of the ground state implies n equals 1, 2 over L sine of n pi x over L, n is 1, is just pi x over L, times h bar over I times d dx. 2 over L sine pi x over L dx. Note that h bar over I is constant, root 2 over L, root 2 over L, all that can come out. 2h bar over IL, 0 to L sine pi x over L times cosine pi x over L times pi L. Yay? But from 0 to L, sine pi x over L, cosine pi x over L, this is gonna be identically 0. So what that tells me is that the expected momentum in the ground state is 0. In other words, it's just as likely to be moving in the plus x as minus x direction. Let's look at the expectation value of px squared. Here, note that px squared acting on psi is just minus h bar squared times the second derivative of psi with respect to x. And so this is just going to look like, well, let me not skip as many steps. 2 over L sine pi x over L times h bar over I. Let me do this a little slower. H bar over I dx times 2 over L sine pi x over L dx. And this just winds up looking like h bar squared pi squared over L squared 0 to L of our original psi star psi dx. If this really is just minus, if this just really winds up being minus h bar squared times d squared dx squared, while taking the derivative of this twice is just going to give me pi squared over L squared, but it'll be negative, but negative negative just makes pi squared over L squared times this h bar squared times psi star psi dx over the whole range should just equal 1, right? And so this is just equal to h bar squared pi squared over L squared. But remember that I thought I had this on this board, but I clearly have it on a different board, that if I really don't have it on this board. E is p squared over 2m, then p squared should go as 2me. And so I expect that this looks like 2 times m times e. Note that gives me that e goes as h bar squared pi squared over 2ml squared, which h bar squared pi squared over 2ml squared is e1, right? Which makes sense because we were looking at a particle in the ground state. Does that make sense that this really should just return to me1? All right. Okay. So a little bit more discussion for us. I wanted to think of, so we've been talking about this wave function as describing or at least psi star psi dx is representing the probability of finding the particle between x and x plus dx. So I wanted to think of an electron wave in a non-relativistic case. And as we've been doing, we can say that psi of x and t looks like, I don't know, a sine kx minus omega t, or a cosine kx minus omega t, or a e to the I times kx minus omega t. We had add phase constants, obviously, but I want to think about what's really meant here. And so we have this kind of standard v goes as f times lambda, frequency times wavelength. But we also have these statements that E equals hf, and we had that P is equal to h over lambda. And so I can replace f with E over h, and I can replace lambda with h over p. These are the de Broglie conjectures, right? But note something cool happens here, right? If I take f times lambda, E over h times h over p is just E over p. Since this is non-relativistic, we can get away with saying that the energy just goes as, kinetic energy goes as half mv squared. But note that that is momentum. Classical momentum is mv squared, quantity mv and quantity squared, m squared v squared over 2m, right? So E goes as p squared over 2m. We'd solve that. The velocity of this electron would be momentum over mass. It's a long way to get to the classical relation, right? If we've been saying that momentum is m times v, then classically v should go as p over m. Probably didn't need to go through that many hoops, but we're there all the same. We could describe the phase speed of this wave as E over p, but if E goes as p squared over 2m, E over p is just p over 2m. But note that that is, pardon, p over 2m is half of the speed of our electron, right? They don't match. So this phase speed is not the speed of the electron. And so that calls to question whether or not it's fair to talk about this really describing the particle if it doesn't have the speed of the particle, right? And so we're going to introduce something called group velocity. In fact, if I want to think of the electron as, classically we've always talked about the electron as a point particle, right? It has a location, a point. But if I was thinking of a wave, right, a single wave isn't localized, right? It extends out in all directions. It extends out along the x-axis forever, right? But I could add to this by superposition of waves another wave that has just ever so slightly different wavelength, and then maybe another, and then maybe another. If I add enough together, I can create a wave packet, right? It takes a lot of waves to do that. But you can think of this as the locality of the electron, right? But it's not one wave, it is many, 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 many waves, all superposed, all interfering to give a localized wave packet. So let's take a look at this one. While we still have E equals HF, we still have P equals H over lambda, I could turn F into omega over 2 pi, right? The angular frequency over 2 pi. This is such, H over 2 pi is such a commonly appearing value that we're going to give it its own symbol. h over 2 pi, we're going to start calling h bar. And so we can also say that E is equal to h bar omega. You remember from physics 130 that we introduced when we were talking about traveling waves or the wave equation, we introduced a wave number k, and we said that 2 pi over k is equal to lambda. And so I could replace lambda with 2 pi over k and see what this gets us. And so if I have h over quantity 2 pi divided by k, that turns into hk over 2 pi. Again, that h over 2 pi pops up. So we could say that the momentum is just h bar times k. Well, you'll also remember from physics 130, hopefully, it's also in your book, or come to office hours. I get lonely. That we could describe this group speed as d omega dk. And so, if omega is e over h bar and k is p over h bar, d omega is dE over h bar, dk is dP over h bar, that over h bars cancel, and I get that the group speed is dE dP. Again, returning to E for the electron is p squared over 2m. dE dP, taking the derivative of this, p squared over 2m, that's 2p over 2m is p over m. Notice p over m, though, is the speed of the electron. And so the group speed of our collection of waves really does travel at the speed of the electron. And so this packet, this collection of waves, provides the localization of the electron. But it comes at a cost. So last week we looked at the kind of classical uncertainty in the position and wavelength. So position times wave number, uncertainty in position times uncertainty in wave number, order 1 for waves. Uncertainty in angular frequency times uncertainty in time measurement, again, order 1. But I could multiply both of these equations by h bar, and then I get delta k times h bar, but h bar k is p, and so delta k times h bar, that's delta p, right? And so delta x times delta h bar times k, that's delta x times delta p. If I multiply this side by h bar, I have to multiply this side by h bar. And so delta x, delta p has to be order h bar. Similarly, if I multiply the bottom equation by h bar omega is e, right? And so delta h bar omega, that's delta e, times delta t is order h bar, right? So I have two uncertainty relationships here. Uncertainty in position times uncertainty in momentum is roughly h bar. Uncertainty in energy measurement times uncertainty in the time over which the energy was measured is also order h bar. You'll see these equations, these are the uncertainty relations. You'll see these written different ways. Probably the most common way you'll see this written is if delta x and delta p, if what you mean by the uncertainty in the position and the uncertainty in the momentum, if what you mean by that is the standard deviation of the measurements, then you get basically a factor half. Delta x times delta p needs to be greater than or equal to h bar over 2. Similarly, delta E times delta T needs to be greater than h bar over 2. There's a lot of consequences from this, to be honest, but let me point out one of them, and then we'll try a couple examples. So first, let's pretend that we're looking at standard deviations. Delta p squared, well, that's p minus p average, quantity squared averaged. But I could take p minus p mean or p average, square it, and I get p squared minus 2 times p average plus p average squared, and then average of all of that. But baked into this is something kind of cool, right? That our particle in a box, if the box is symmetric, I guess that's how I want to put this. We've already seen that we expect the momentum to be 0 on average, right? It's kind of what we meant by this. And this was a fairly symmetric idea, right? But that means that this p bar and this p bar are 0. And so what we get is that this term 0, this term 0, it's just p squared averaged. So delta p squared is equal to the average of p squared. I'm going to write that with just a big bar over the top of p squared. So I don't mean p average squared, I mean the average value of p squared. But if we come back to this statement, delta p times delta x should be order h bar. So delta p should be order h bar over delta x. If our box has length L, like what we had over here, then delta x, I know it's somewhere in the box, just to really roughly approximate this, delta x could be as big as L, right? And so that tells me that delta p squared or p squared averaged has to be greater than h over L quantity squared. But again, coming back to this idea that E goes as p squared over 2m, if I look at the average value of p squareds and divide that by 2m, that should be the averaged energy. That tells me that the average energy needs to be greater than or equal to h bar squared over L squared divided by 2m, right? H bar squared over L squared divided by 2m. But note, what we're seeing here is that there's, just by putting this particle in a box, we are insisting that there is some minimum energy that particle has to have. So that, I know that's kind of fast. Thankfully, this is recorded. Hopefully it's recorded. Maybe not hopefully, but let's try some examples. So let's look at something small but still macroscopic. Something that has a mass of 10 to the minus 6 grams, that's tiny, right? But not nothing. In a one-dimensional box that has a length of 1 micrometer. So if we have that E goes, let's say min. if we have that E min is going to go as our h bar squared over 2ml squared, well, that's 1.055 times 10 to the minus 34 joule seconds squared over 2 times the mass, 1 times 10 to the minus 9 kilograms. Let's do this in SI. Divided by 1 times 10 to the minus 6 meters squared. I hear my phone. I hear my phone, but I don't know where my phone is. So $1.055, well, here. Squared divided by 2 divided by 1x 9 negative divided by 1x 12 negative. And I'm getting about 5.56 times 10 to the minus 48. Those are joules. Tiny, 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 tiny number, right? If we wanted to find the V that goes with this, that would be, well, coming back to our half mv squared V is going to be 2e over m under the radical. So 2 times 5.56 times 10 to the minus 48 joules over 1 times 10 to the minus 6, minus 9 kilograms. So times 2 divided by 1x 9 negative, square rooted, getting about 1.05 times 10 to the minus 19. And those are in meters per second. You can see that even for a small, and this is really small, right, macroscopic object in a very small macroscopic box, right, 10 to the minus 9 kilograms in 1 micron of well, the speed of that is far too slow to measure, and the energy of that is far too small to measure. But let's look at an electron in an atomic scale one-dimensional box. Atomic scale, because a good rule of thumb is an angstrom is a good atomic scale number for lengths. So cheating a little bit, if we have that the E min is h bar squared over 2m L squared. I'm going to multiply top and bottom by c squared. Right, no harm, no foul. and we get h bar c squared over 2mc squared L squared, while h bar c, known value, 197.3 electron volt nanometers. We're going to square that. We're going to divide it by 2 times mc squared for an electron is 0.511 mega electron volts. Times 0.1 nanometers squared. Note that I have electron volt nanometers squared in the numerator. And I'm going to have, so numerator electron volt squared, nanometers squared, denominator I'll have electron volts times nanometers squared. That will leave me with electron volts. And so, (197.3) squared divided by 2 divided by 0.511 x6 divided by 0.1 divided by 0.1, and I get about 3.8 electron volts, which is not terrible. That is, that is on the order of energy levels for electrons in atomic scale problems. So there's something to this, I guess, is what I wanted to get at. So the last one that I wanted to try with us today. So for atoms that are brought to an excited state, most of those excited atomic states will decay by emitting a photon within 10 to the minus 8 seconds. And I'd like to assume that that's true and find the minimum uncertainty in the energy and the frequency of the emitted photon. And so I return to the statement that delta E, delta T, I'm going to let be roughly greater than or equal to h bar. And so if I think of this as kind of the time window in which this could happen, I'm going to think of that as the possible uncertainty. I'm going to say that delta E should be greater than or equal to h bar over tau. And so h bar, you remember from lab, 4.14 times 10 to the minus 15 electron volt seconds over 1 times 10 to the minus 8 seconds. Oh, that's h, right? I also need to multiply by 2 pi, right? Because h bar is h over 2 pi. Sorry. I don't need a calculator for that, but I do need a calculator to do this problem. So 4.14, 10 to the minus 15, divided by 2x 8 negative equals divided by shift pi. I'm getting about 6.58 times 10 to the minus 8, actually 6.59. And those are going to be electron volts. Yay? So this would be, as I've solved this, right, delta E min, since that's the greater than or equal to here. If I wanted to find the similar for F, we could say that delta E times delta T, I don't know how I'm going to fit this all. That delta E times delta T is going to look like H times delta F times delta T, right? Delta E, E goes as HF, so delta E goes as H delta F. And we want this to be, again, roughly greater than or equal to H bar. We could say then that if I divide across by H, H bar is equal to H over 2 pi. So delta F, delta T should be greater than or equal to 1 over 2 pi. And so delta F should be greater than or equal to 1 over 2 pi times 1 over tau. And plugging in values, one over 2 pi times 1 over 1 times 10 to the minus 8 seconds. So 1 exponent 8 divided by 2 divided by shift pi is about 1.59 times 10 to the 7 hertz. So that tells us that the emission of a photon, if it occurs within 10 to the minus 8 seconds, we have some uncertainty in the energy of that photon, which goes to 6.59 times 10 to the minus 8 electron volts. We also have some uncertainty in the frequency of that emitted photon. That is why when you look at emission lines, they aren't perfectly thin, they actually have some breadth to them. Questions, comments, concerns? Did that sort of make sense? I rushed through that a little. Hopefully that made some sense. If you guys have questions, please feel free to ask. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.